what we're going to talk about today is ultrasound and how it applies. And there's several different things that we're going to do. There's hundreds of things you can do with it if you don't limit yourself, okay? So what we need to do is think outside of the box. And we've heard that this week. We've heard it a couple of times. Since we were born, we've been taught, if I can't hear it, I'm not afraid of it, okay? If I can't see it, I'm not afraid of it. How many times when you hear something that startles you, you cover your ears, or automatically you cover your eyes, because if I can't see it, I don't worry about it. We've been trained that way since we were born. We have to get away from that. We have to start thinking outside of that box that we've been trained in all of our life, because there are things out there that we can hear, and there are things out there that we can see if we extend our senses, which ultrasound is an extension of our senses, actually, because we're listening at 25 to 40,000 hertz. Our ears can only hear 16.5 and down. How do we know a dog whistle works? Well, the dog either comes to you or he don't. You know, I could give you a drinking straw and tell you it's a dog whistle. If you blow through it, might work, might not. But that's technology that's above our ears. We can't hear the dog whistle, but they do work, because you watch the dog, he'll either come or his ears will perk up. The deer signals that go on the front of your car, they make a whistle that the deer hears out ahead of you, and he runs him off the road. In Kansas, that's a big deal. I've hit 3 deer in the last 2 years. That's a big deal in Kansas. It's very dangerous. So there are things that happen that we can't see or we can't hear. And so we have to be able to think outside of that box. And we have to start using our imagination. With this technology, the only thing that holds you back is your imagination. Now, I've talked to a lot of guys, and they say, nah, I don't believe in all that technology. I don't believe in that stuff. But you know what? When I first started speaking, and I'm talking pretty loud, I normally do, because when I first started speaking, we didn't have lapel microphones. I mean, I'm wired up like a robot up here, okay? And what about cell phones? If you wanted to make a telephone call 10 years ago and you're going down the road, you had to stop at the 7-Eleven and put a quarter in a payphone. Try to find a payphone today, okay? They're just not around because of technology, the way it has advanced. Now, I talked to the guy that says, I don't like technology. He don't know how to send an email, but you can't take his phone away from him, because he'll tell you, oh, I got to have my phone. So then what I suggest is, in a lot of cases, because we don't think outside of the box, because we don't let our imagination go crazy with us, what happens is we only accept the technology that we're comfortable with. The telephone, anybody knows how to use a telephone. But if you're not comfortable with the computer, you shove them away. If you're not comfortable with listening to ultrasound, you don't do it. You leave it up on the shelf. If you're not comfortable with what you're seeing or understand what you're seeing with infrared, you leave it up on the shelf. Worst thing that can happen. We got $60,000, $70,000 worth of equipment sitting up on a shelf. That's a big investment to use once or twice a year because you're forced to. What I say is we should use it every day. Every day it should be used on something. So let's move on, and we have to remember to think outside of the box. I just went backwards again. Okay, non-intrusive testing is exactly what we're talking about. Okay, we don't have to touch it with ultrasound. We do. We don't have to touch it with infrared because we can see it through the camera. It's all non-intrusive. We touch it or look at it with the instrument and record and run our test. We do not shut the machine down. I usually set a base. I want the machine running under as near a minimum of 40% load as I can get it, because I want to test it in operating mode. I don't want it sitting there idling, because that's not the way it runs when it's operating. Now, we talked yesterday about some variable speeds. CNC machines, for an example, you can't run those when they're, you can't test those when they're in operation because of the noise of the cutting tools. So we run them empty, but we set every one of them at 1,200 RPMs. That's it. We know every test we run on a CNC machine is run at 1,200 RPMs. So now we have the trend. I can't come in here today and run it at 1200 and then come in tomorrow or next month and run it at 2200. We're not comparing apples to apples. Apples to applesauce, but it's not the same thing. So you can't do that. So, okay, and also it's safer and there's less cost in non-intrusive testing. I have used ultrasound on every one of these, any one of these applications. And there's probably not very many people in here there's some of these you haven't even thought about, I'm sure. But I've used ultrasound on every one of these applications at one point in time or another. And I'm not going to sit here, or I'm not going to stand here and bore you with going through each one of them. Does anybody have any question about any one of them, about what we done or how we done it? Again, you just let your imagination go crazy. That's what you have to do. You have to think about, how can I make this work? Because if you think about it, you can make it work. Okay? Anybody have any questions? Oh, you want to see a chart of partial discharge? We'll have one. We have one coming. Okay? Okay. So in order, and I'll answer your question as soon as we get to it. We have a chart coming up that shows that. Okay? So in order for us to start making some tests, in our application, we require some things of the business, okay? We have to make a motor ready for service. I can tell you right now, 80% of the motors that come out of the shop have dry bearings in them, okay? The first thing we have to do is pull the grease tubes. It's the pipe that runs down in front of the motor, down into the bearing. Invariably, a new motor or rebuilt motor, unless you've made arrangements, that pipe is going to be empty because they do not grease the motors coming out. The reason they don't is because moly-based grease and poly-based grease are not compatible. You mix the two together, they form an acid that will eat the races out of your bearings in 3 to 5 years. Well, they're not going to tell you that. And they don't know what kind of grease you're using, so they don't put anything in there. So now you get your motor, you set it up, hook it up, operating, we're off and running with dry bearings. Before you realize that problem, then we go and grease them, and it's too late. Now, the book says we give it 2 or 3 strokes every 3 or 4 months. So by the time you get that grease tube full and actually get grease to the bearing at 2 or 3 strokes every 3 or 4 months, you're 3-5 years down the road and your bearings are already shot. Okay, so now I get to sell you a new motor. Built-in job security. It happens. Okay, we insist on a shaft run-out test. A shaft run-out test, for those that don't understand, what we do is we put a magnetic stand on the motor or down on the base, take a dial indicator and put it on the shaft. Start at the keyway, turn it over real slow till we get to the other side of the keyway. If that dial indicator moves more than 3/1000ths of an inch, I send the motor back. I will not accept that motor. And we're going to get into some alignment in a little bit, but any motor that we align, we will not walk away unless we have it down to less than 3/1000ths of an inch alignment. Now, what I say is, if it starts out 3/1000ths off this way, when you roll it to the other side, it's 3/1000ths that way. So now we have a 6/1000ths variance. There's no way you can align it to 3/1000ths if you're 6/1000ths out to start with. So don't accept the motor. I'm not taking it. Send it back. Okay? The next thing is a bench vibration test. I used to do vibration for one oak. I don't do vibration anymore. I can give you the same results quicker, cheaper, and more accurate with ultrasound. And we're going to get into that. The next thing is an amp draw test. Most people do not do an amp draw test when they first install a motor. That is the most important time to do an amp draw test. When it's under load and it's brand new. If each phase is pulling 9 amps and a year down the road I start to have trouble with that, and if I take an amp test then and the C phase is pulling 22, that tells me I've got a problem, because when it was new, this is what it was doing. Now it's not doing that, so I've got a problem somewhere, okay? It's just another indicator. So that amp draw test is very, very important. We do that on all of our facilities when they put in a new motor. That's one of the things that has to be done. Okay? So let's move on. Where are the correct points to test? The reason I put this in here is because the terminology is very important. If one of my staff calls me or one of my clients calls me and says, look, I have the Gearbox inboard A bearing making a lot of noise on pump P23, I know exactly where he's talking about because his terminology and my terminology are identical. Okay? And you'll notice on here we have MOB. This is actually what I put in the gun on the route. We have MOB as a motor outboard bearing, MIB as a motor inboard. It's pretty simple, pretty cut and dried. Okay? The gearbox inboard, gearbox outboard, pump inboard, pump outboard. Okay? How would that look? Well, if I can find it. There it is. Okay, you can see there the motor. We always start at the fan end of the motor and we go as the power flows. Okay? That's the easiest way to remember it. So if I start at the fan end of the motor, which is here, that's the motor outboard bearing. Obviously then this is the motor inboard bearing. Pump inboard bearing, pump outboard bearing. On a horizontal pump, your two inboard bearings are going to be together. The two outboard bearings are going to be apart. In, out. It's not that hard. So now any one of you call me and say, I've got a motor inboard bearing that's making some noise. I know exactly which bearing you're talking about. We're not going to lose it in what we can mix up. So let's look at one then that's let's look at a gearbox. I'll try to get it up here if I can get. Windows 7 was not my idea, okay? Okay, so what we've done here, we've still got the same points that we had, motor out, motor in, pump out. But what we've done is put a gearbox in it, in that line. Now, the inboard side of the gearbox is always the A side. The outboard side of the gearbox is the B side. So I have a gearbox inboard A, B, and C. Gearbox outboard A, B, and C. Okay? Then we go into the machine. It's pretty simple, pretty cut and dried. When we use, if we can get everybody using the same technology, whether this is the best or not, I don't know. It works the best for me. It works the best for our staff. I have 3 techs out in the field, and when they call me and say, Chuck, CM8 motor inboard bearing is making a lot of noise, I know exactly where he's at because there's no question of, and we're going to look at that bearing before we're done. Okay, if that applies on horizontal pumps, what do we do about a vertical pump? Okay, the vertical pump, everything's down in the ground. And it may be 20 feet down, it may be 5 feet down, it may be 200 feet down. So what we have there is we have a motor outboard bearing. Remember, we're talking about the fan first as the power flows through the machine. So we have a motor outboard bearing, a motor inboard bearing. The pump, we just have to take a reading with ultrasound on the pump because it's going to tell you one of 2 things. And we're going to listen to that to a vertical pump in a little bit, and I don't want to give it away. So let's take these off. And so now we've got our terminology where we know. So if I start talking about a certain bearing or a certain motor on a machine or a certain point on a machine, we're all going to know what it is. So now, when I make up my route for my ultrasound, I'll have CM9 as my heading, and then I'll have the points underneath it. And I can tell you right now, if it's a 2-shaft gearbox, the machine's going to have 8 points. If it's a horizontal pump with no gearbox, a direct shaft coupling, it's 4 points. I know that. So now I can make my route up like that. I can walk through the plant. Whoop, there's a horizontal pump. It's CM8 is the number of it. And I put a 4 behind it for parentheses, and I move on. I can write up 800 bearings in about 45 minutes by using that terminology. So now we've cut time way down. Time is expensive, okay? So let's move on. Some problems that can be detected with infrared or ultrasound. Does everybody know what a soft foot is? Is there anybody that doesn't know what a soft foot is? Okay. Let's take this right here, okay? It's milled, it's machined flat, right? Each corner is a foot on your motor. If we set this down and this one is up a little bit, actually what happens when you bolt it down is you put a twist in the motor case, okay? What we need to do is shim that up so that when we do bolt it down, it goes down square. What happens is the motor generally is milled pretty good, but the base that we set it on is poured concrete, it's steel, it's warped, it's settled over time. So soft foot should be checked very regularly, okay? Now, what do we have, or how do we know we have a soft foot? Ultrasound can tell us, and so can infrared. There's another way of checking. Obviously, you loosen the bolt and put a feeler gauge under it. See if you can get anything under there. Okay? But what we're going to do is we're going to look at the infrared. See the hot spot on the motor? For you guys over here, right here's the hot spot in the center of the motor. Right here's the hot spot. The problem with this is a 300 horsepower motor, $22,000. Okay? And they put a twist in the case. The rotor tolerances in the center of that motor are so tight that when they twist the case, it shortens that down and it gets hot in the center. This is not out on our bearings. It's in the motor. Okay? Now, what happened is we found that foot right there on the motor had a 10 thousandths soft foot right there. When we loosened that bolt, the motor come up 10 thousandths on that foot. So actually what they'd done was they'd bolted 3 down, then bolted that one down. They forced a 10 thousandths twist. 10 thousandths is not very much. It's not very much at all. I have some business cards laid up here. I had these mic'd. These are 6 thousandths of an inch thick. So now you can kind of imagine what 10 thousandths is. It's not very much. But what happens? What happens when we have a 10 thousandth soft foot? Where you at, Chuck? Okay, what we're going to play is that soft foot. I want you to listen for the surge. It's you're going to hear the surge. Okay, are we ready? Here we go. You hear the in there? That is that rotor working through a twist. Okay? Also, if we look, we have our 60 cycles in here. So that's electricity. 60 cycles. It's electricity. It's just that simple. I'm sorry?
The motor, at what point are you testing or using a UE where I can get that sound?
To get this, right there in that, on the motor inboard bearing. Okay? Yes?
Can you repeat the question so they can hear?
Okay, I'm sorry. He asked me at what point was I checking the motor with the ultrasound gun. I had it placed on the motor inboard bearing, right above that foot. Okay? Yes?
Was it before the infrared or after the infrared?
The infrared is how I actually found the soft foot. Okay? Yes?
What was the RPM on the motor? What was the RPM or turning speed?
That one turns 1735, 1750.
That would be a 2 times right there, which will also indicate soft foot.
Yes, yes. Okay? Now, let's correct it. Okay? We correct the soft foot. So let's go back. If I can find the mouse. We're going to open the wave. I got to stop it. Spectralizer was not my idea either, guys. Okay, so now we're going to correct the soft foot. Listen to the difference in the sound. Can you turn that down a little? The surge is gone. Okay? That was a matter of about 20 minutes. We found that. We started checking the feet and found the 10 thousandths. We put 10 thousandths under it, bolted it back down, and that's the sound we got now. Okay? So soft foot, very, very important. That should always be checked. Okay? Always check. Yes. If I can.
Find it. Stop.
The first one. Yes. Hear the surge in there? Yes.
If you would have listened to the outboard, would you have seen it?
I think you might have. I didn't, but I think probably you would, because that's going to be throughout the motor, because it's coming off of the rotor. Okay? Yes.
You look at the attitude, it's in harmonics. When you look at the one after you fix the soft foot, it's not in harmonics.
It's gone. The soft foot's gone.
So it's turning, you're getting into the 60 cycles.
Yes. What we're getting into is the electricity of the rotor is rubbing on the outside of the case. Okay? Okay, so let's move away from this one.
One more question.
Okay. Yes.
Is there any specific frequency you can refer to detect this soft foot?
Is there
Any specific frequency?
I'm sorry, I can't hear what he's saying.
What frequency do you have?
Oh, frequency? Yeah, it's 20. I test all my contact bearings at 25 thousandths. So that's where I was at on there. It was 25 thousandths.
Yeah.
25 hertz. 25 hertz. Yeah.
Kilohertz.
Kilohertz. 25,000 hertz. That's where I got 25,000. Okay. Kilohertz. Okay. Okay. Let's move to the next one. If I can find. See, all this technology, and I got stuff laying everywhere, and I lose about half of it. So I got to get back on that screen. Okay. Misalignment. Misalignment, shaft to shaft misalignment is the number two cause of premature motor failure. The reason for that is when you have a shaft to shaft and they're out of a line, it's like trying to turn a hinge. All of the stress goes back to the inboard bearings. Okay? We cannot have that stress on those bearings because that's going to make them fail. And it's a simple thing to do to align them, but you have to do it right. I have guys that say, yep, it's in a line. I say, how did you align it? And they say, with two squares. Okay? They put a square here and it comes out and they both turn in. If these out here are even, that's in a line. No. Remember, we're talking 3/1000ths of an inch. Okay? So it's got to be in a line, center to center, half the thickness of this card or less. Okay. So it's very, very important that we have the alignment where it needs to be. Okay, what is misalignment? Misalignment is, again, where the center line and center line are not collinear. They're not running together. One's here. Okay? And we're going to see some pictures of that. How would we find that with ultrasound? How would we know? Does anybody have an idea how we would know? Oh, yeah, I told you. Okay. Remember our 4 points. Motor in, outboard, motor inboard, pump outboard. The two center readings are going to be louder than the two outside readings. Anytime I find that situation, the first thing I check is alignment. Okay? Because of the stress that misalignment is causing, those bearings are going to be louder. Now, in some cases, they may not, the pump bearing may not be as loud as the outboard bearing on the pump because of cavitation or some other things. So we have to listen to what we're listening to. We have to hear what it's telling us. Okay? Now, just that one thing alone is not going to have me shut that machine down and go to realigning it. Okay? That's an indicator. I'm using the ultrasound as an indicator. Now I'm going to take my infrared and I'm going to look at it. What should I see there? The two inboard bearings are going to be hotter than the two outboard bearings. Okay? Well, I wonder how that would happen. Here's misalignment. You see what's happening here, and a lot of people don't understand it and don't realize how important it is until we see something like this. These machines are not going to last very long. Because how many of you have tried to open a gate when the hinge is crooked? The gate's hard to open because it's bent. That's what we're doing with the motor. We're trying to open that gate, but we're doing it at 1700 RPMs. And then we wonder why it shakes. Okay? Misalignment. Very, very important. This is the old way to realign them. What this is called reverse angle alignment. The bottom one is tied to this shaft, and it's got a dial indicator on the other shaft. The top one is tied to this shaft and got a dial indicator on the other. So when you roll it over, it's measuring this. Okay? You want those to be at 0. This is the cheapest way of going. It's not as fast as lasers. Lasers are a lot better. I do everything now with lasers. Okay? And we'll have some examples of that here in just a little bit. Okay, here we go again. High vibration levels. Now, let's think about this. Ultrasound tells me my 2 inboard bearings are louder than my 2 outboard. Infrared tells me my 2 inboard bearings are hotter than my 2 outboard bearings. I put my hand on the motor, and it feels like a vibrator. I got 3 things telling me here that this thing's misaligned. At some point in time, we need to make a decision to fix the machine, or the machine's going to make a decision. And they don't have any conscience. They don't care. I guarantee you it's going to go down at 2 o'clock in the morning when there's no staff here. We got to call all the staff back. 4 inches of snow on the ground and 50-mile-an-hour winds, except in Brazil. They don't have that. Okay? But you understand what I'm saying. Nobody ever lost a motor when they didn't need it. If you don't need it, it ain't running. Okay? So we always lose them when we're working them the most, pushing them the hardest because of production. That's when logically, that's when they're going to fail. So now what we have is we're hurrying. We're taking shortcuts. We're trying to get back up and running because we're losing production, and management's out here on your backside trying to get you going. And now it becomes unsafe. Now we start to lose fingers because we're not doing things the right way. We're taking shortcuts. We don't do near as good a job of alignment because we're in too big a hurry to get it back to running. I say we take the time. Let's do it right to start with. Then we don't have to double the time because we're going to end up doing it again. Okay? I can't even see that. Oh, this one's hard to see. But if you look at this motor, right here's the inboard bearing on the motor, inboard bearing on the pump. If we look at that, it doesn't look like there's a problem. I don't see anything wrong here. But if we look at it with infrared, it's pretty evident, pretty fast. Okay? Misalignment. This is a classic case of misalignment. I have a couple examples of this, so we'll look at another one here right quick. Again, this is lined with lasers. This is that machine we just looked at. When we first put it on there, you can see it's 27 thousandths out of alignment there, 21 thousandths out of alignment there. Alignment is both this away and this away. Okay? So we have it side to side, up and down. You can see the feet on the motor here, and you see the motor here. This is actually the coupler. 195 thousandths, we have to raise the back of that to get it. 195 thousandths is 3/16 of an inch. That's a ton. That's a ton. No wonder this thing is hot, right? So when we got done aligning it, this is the way it's set. That 5/10 is 5/10 of 1,000th. That's how close you can bring them. I literally could take a glass of water and set up on top of that motor, and you don't even see a ripple in the water when it's running. You have to put your hand down there to see if there's air blowing to even know it's running. They run that quiet when they're aligned right. Okay? Okay, let's look at another one. This one here is a Martin-style coupler. We've all seen the Martin-style couplers. It's the coupler that goes together, and it's got the rubber in the center of it that looks like a gear. And that's what makes it turn, okay? So this coupler, what happens is this thing was so far out of alignment, we've all taken a piece of wire before and bent it until it broke and it got hot. That's what's happening here. These two hubs are doing this. That's so far out of alignment, the motor's about to jump off of the base. So again, the two inboard bearings were louder than the two outboard. So we look at it with infrared, and it's pretty obvious. Look at that coupler. There's no reason for that piece of rubber in the center of that to be hot other than misalignment. That's all it can be. There's nothing there to heat that rubber up. But you can see the bearings on the pump and the bearing on the motor are both hot. Classic case of misalignment again. So we realigned this one, and here's where we go. It was 91 thousandths out. See the difference in how it came back in once we put the lasers on it. You put the lasers on it, it's about a 45-minute job to align it and get it right. Now, 45 minutes to get it right and make it run 10 years, or don't take 45 minutes and get it wrong and have it run 18 months. Don't take a rocket scientist for me to figure that one out. If I can keep from doing it every 18 months and do it once every 10 years, that's the way I want to go. I'm lazy by nature. So, okay, so misalignment is very, very important. It's things that we have to really think about, again, and we're using our technology to find those problems. Didn't used to be that way. Used to be you put your hand on it and say, it's not bad, or you put your hand on the pump, it ain't bad. You know, that human thermometer thing's not a good deal. It's not a good deal because, again, now we're breaking that plane. And sometimes you put a hand in there and you pull part of a hand back. That's not a good deal. We don't want to go there. Okay? So misalignment, we have to pay a lot of attention to that. Okay, here's a simple question. If misalignment is the number 2 cause of premature motor failure, what is number 1?
Lubrication.
Close. Improper lubrication. Okay? How much grease is enough? How often do we grease? The book says we give it 2 or 3 squirts every 3 months. Well, what I'm saying here is Mark is a motor and he runs 24/7. Okay? Bennett's a motor right here and he's kind of lazy. He only works 2 hours a week. We're going to grease them both the same? It's not even logical. It doesn't make sense. We're going to undergrease this machine, and this one's going to be deadly overgreased if we do it what the book says. So I say throw the book away. Get rid of it. We don't need it. Start using ultrasound. Use the equipment we have to do it. I grease bearings with ultrasound totally. And a lot of our clients, they do not grease motors. My staff does it. We have taken over their grease program completely. Because there are some things that we require. We talked about it on the motors a while ago. Okay? How often do we grease? What type of grease do we use? How many of you are using all-purpose grease in your plants? Boy, am I glad to see that. You know what? All-purpose grease, Mystic JT6, that red stringy stuff, that's made for a plow out on the farm. Okay? We need to be in a Polyrex SHC 100, something like that, that's a high-speed grease, a high-temperature grease that's made for electric motors. We can't use the same thing that we use out on the farm and just pump grease in it till it oozes out, because that's what we used to do, and we've been raised to do that. When we do that, all we're doing is pumping the dirt out of the bearing. We're not re-lubricating it. It's got enough lubrication in it. But if we pump grease till it oozes out, then we're forcing the dirt out of the bearing. That's all we're doing. We've over-lubricated it. Okay, so what does ultrasound do for greasing? It stops you from over-greasing. It stops it. We can grease a bearing. The bearing will tell us when it needs grease. It will tell us when it's got enough grease. So we quit. Okay? They say, well, what equipment does it take? Obviously, I use a 10,000. Haven't used the 15 yet. Sounds like it might be a pretty good deal. But it will show us the same thing. It will show us the same thing. So, let's move to a bearing then. What happens here? If you look at this motor, right there, you see grease coming out of it. right here. Okay? The problem with that is it's been overgreased. What happens when we overgrease a motor? We have any electricians in here? Good, then I'm not going to get in an argument. Okay. Contrary to popular belief, electricity doesn't go through the wire. Okay? It goes around the wire, around the outside of it. Okay? That's how we measure how much current is going, because we put an amp probe around the wire and measure the magnetic field. Okay? The bigger the wire, the more surface area you have, the more current you can run through it, and it stays cool. The smaller the wire, the less current. Also, contrary to popular belief, insulation is not to keep you from getting shocked. It's put on there to direct the flow of current, to make sure it's going the right direction. Okay? So now, if we overgrease our motors, what happens here is the grease builds a tunnel. It builds a tunnel. It starts working to the outside. As the balls are going around, it builds a tunnel in that bearing. So now the balls in that bearing are running in this tunnel. It can't dissipate the heat. It can't get it out of there. It becomes an insulator. So pretty soon it gets hot enough to melt the base down of your grease, and then your oil starts to sling to the outside, and we start to get leaks around our motors. And everybody here's got one of these. And if you don't, if you say you don't, we'll go find you one. Because everybody does this. Okay? So now that it's hot, it's starting to lose power. We're losing RPMs. It's not carrying the load it did. What's the first thing we do? Pump some more grease in it. Invariably, that's what happens. The first, oh, it's getting hot, let's grease it. Well, the reason it's getting hot because it can't get no air. Okay? I asked the guy, I said, how much grease do you put in it? He said, well, it's a 25 horsepower motor. I said, okay, how much grease do you put in it? He said, I told you it's a 25 horsepower motor. Okay. We all got these. Same scenario. It's leaking out. It's coming around the end bell. It's being slung to the outside, centrifugal force. 25 horsepower motor, how much grease do you put in it? He said, well, it's a 25 horsepower motor. I said, so what? He said, you don't understand. 25 horsepower, you put 25 strokes in it. What do you do with a 600 horsepower motor? Pump a 55-gallon drum in there? Now, y'all think I'm kidding you. Here's that 25 horsepower motor. Look at that. That's unreasonable. Look at the grease. No wonder the motor's getting hot. Okay? This happens every day. Every day. I found this one in Wichita, Kansas, about 40 miles from where I live. Look at this. Look at this. Oh, man, I'm telling you what. After about the 8th tube of grease, the light should have come on. Where's this stuff going? You know? Number one, this guy would not be working for me anymore. If you ain't smart enough to figure out 6 or 8 tubes of grease is enough in this motor, then I don't want you working here. Okay? The other thing, notice the bearing. Look at that bearing. It's a shielded bearing. You couldn't get grease in it if you wanted to. So why does it have grease zerks in it? Well, the maintenance man in his infinite wisdom goes out and looks at the motor, hears it rattling a little bit and says, boy, that needs some grease. So he pulled the plug out and put a grease zerk in it so he could put grease in his motor. So they pump grease and they pump grease and they pump grease, and it never quieted down, and they keep pumping grease till finally messed it up. It's gone. Okay? In my clients, I will not have a motor with shielded bearings in it. Okay? The reason for shielded bearings is to keep you from overgreasing, because that's what happens. Okay? Now, in my situation where I have to have the plant running 24/7, I want to be able to at least, if I find a bad one, I'll put some grease in it and I'll baby it along until I can get to a scheduled shutdown. But if it's got shielded bearings in it, I'm at the mercy of that bearing. There's nothing I can do. I just have to hope it lasts until we can get to a shutdown. Okay? So I will not have shielded bearings in any of my motors. The first clue of a shielded bearing is they pull the grease zerk out and put a pipe plug in there. Okay? So if I get one back like that, it goes back to the factory. I don't want it. I don't want it. We're not going to have it in my plant. And that's very, very important. Very important, especially when you're in charge of greasing all the motors. I've got plants that have 500 motors in them. And we grease those motors, but we only grease them when we need to. Okay? We throw the book away. We're not going to grease every 3 months because it says to. So let's grease a motor. This is a 200 horsepower motor that's been sitting on this stand for probably 15 years. Okay? It's a deethanizer bottoms pump. This pump pumps 1,500 pounds of pressure, and it's boiling propane. What happens is it pumps... Yes? She has a question. The microphone? Oh, here, I got it.
There we go.
Si soy nueva en mantenimiento y no sé cómo están los motores.
I'm sorry, I can't hear her. Let me move back by him.
If she's in maintenance, if she work in maintenance.
If she's new at maintenance,
Yes.
at that plant, and she doesn't know anything about those motors,
Okay.
then, entonces,
¿Cómo voy a saber
how will I be able to know,
si le falta o está bien de grasa?
okay, if I'm new at that plant, how do I know there's no grease in that motor, or if it needs something?
Very good question. Very good question. So, let's grease this motor. Okay? So what we're going to do is I'm going to pull this back over onto the screen. We'll go to File. I better go to Stop. Hey. Hey, Gary. You see what's going on here, don't you? Okay. Okay. We're going to grease that. We're going to listen to the motor first. And when we listen to this motor, a good bearing should sound like air escaping. Shh. That's the way it should sound. It shouldn't sound like popcorn. It shouldn't sound like marbles in a bucket. Okay? So let's listen to this bearing. Okay, you can hear the crackle in there. That motor needs greased. When you hear that crackle, it's dry. What's actually happening is you're hearing the grease that's in there separate. That's what's making the pops. Okay? So, let's grease this motor. We're going to listen to it. As we grease it, listen for the change. Listen for the change. That's the main thing. Okay? So, let's stop. Ah! It takes an old dog a while, but he'll learn the trick after a while. Okay? I will never overgrease another bearing. Doing it with ultrasound. We
You
hit.
have some OverGreaser bearing sample.
Yeah, that solves the problem right there. Yeah, ultrasound just solved my grease problem. That's why I grease the bearings in the plant and their maintenance people don't, because they don't have ultrasound. This bearing told me it needed grease, and it told me when it has enough grease. So quit. It ain't going to get no better. Do you have a question?
Yeah, Chuck, I think.
Get the microphone there.
I think the gentleman's question was, do you have a sound file of an over-greased bearing?
Of an over-greased bearing?
Yeah.
No, I don't. Because we don't over-grease bearings anymore.
I have a question. See, you say number one. See, you say number one is over lubrication, number two, misalignment, right? So you have a misalignment, it's going to produce heat in the bearing.
Yes.
And the over lubrication is going to produce heat too.
Yes.
So when do you know if it's over lubrication or misalignment?
Your two bearings. You listen to the sounds.
Right.
Okay. And then.
But I'm the guy in the plant. I don't have anything. What I do, like you say, just pumping, 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 pumping. In both, they have over lubrication.
Right.
So how do you know if it's misalignment or over lubrication?
Over lubrication is going to sound like a good bearing for a while. Okay. Now let's say this. Over lubrication. Let's say we've got a pit in the bearing. Okay. Every time that ball goes around, it hits that pit. Over lubrication on a bad bearing is going to clean that out as it turns, and it's going to come back and start making noise again. Okay? Over lubrication is a bearing that sounds good because we've got it so packed full of grease it can't make any noise. So that I would caution on that. If it's hot, both bearings are hot, then I'm concerned with misalignment. If one bearing is hot and the other one is not, then that bearing's probably over lubricated. For an example, a horizontal pump. Let's take a horizontal pump. We have a motor inboard and a motor outboard that we grease. Most likely the pump is an oil bath. It's got oil in there that turns, okay? So we're not going to over-grease that one. It might not have enough oil in it. It may be low. But usually you can differentiate if you listen to what it's telling you. That's the key. The key is trust the equipment. Listen to what it's telling you because it's telling you what you need to know. We just have to interpret what it's saying. Okay? Let's grease another one. I think I have another one here.
Chuck.
Yes.
Chuck, sorry.
Go right ahead. I can hear you. I just want to...
So what you're saying is this. Sorry.
So what you're saying is this. I think further to what Hugo is asking, what you're saying is this. An over-greased bearing can be misinterpreted as a good bearing.
Yes, it can.
But you have to use the other thing, like a doctor, you actually look for the symptoms, and if the symptoms does not seem to point towards it, then it's not. Right?
That's right. That's right.
Thank you.
Okay, it's just an indicator. Anything we talk about here today, remember on the misalignment, I said I heard the sound, and that would indicate possible misalignment, so I go to something else to confirm it. My infrared confirmed that it was noisy. Or I may take vibration and put on there. I don't do vibration anymore, but I may have somebody come do that. And if vibration tells me 1.5 to 2 times turning speed, there's a big spike, then I'm talking misalignment. So one confirms the other. That's the whole idea of using them all together. Mike.
Another thing on the over-lubrication, and I'm sure a lot of our UV guys can talk about this, is that a lot of times you'll hear an over-lubricated bearing. It just sounds a lot like cavitation.
Yes.
With that popping sound. So, in other words, what you can also do is you can grease that bearing. And if that total quality doesn't change, your decibels don't change, it doesn't see that drop, that's another indication to say that bearing is already
over-greased. Yes.
So there's your other indication along with.
Okay, and I think you had a question.
Basically, if you find a problem and you're diagnosing a problem, you must use a combination of procedures.
Yes.
That's typical common sense.
Yeah, that's the most important thing. You know, and I'm not sitting here trying to sell equipment or trying to tell you one way or another. But if you have the advantage of being able to confirm one with the other, do so. Do so. Some plants I go to have an ultrasound tech, and they also have an infrared tech, and the two don't cross. Because one, you're entering my turf, and I'm better than you are, and I don't want you coming over here telling me that I don't know what I'm doing. Worst thing that can happen, these guys need to work together. Because we can prove right here the two together is what makes it work. Let's listen to this bearing. That's on a 600 horsepower motor. Okay? It's CM8. It actually is on a gearbox that runs a compressor that turns 13,800 RPMs. So it's a very, very important motor. So we greased it. Now when we grease this one, I want you to listen to the end because my tech didn't do a real good job of recording and catching it at the right time. But listen to the end. Okay? Oh, come on, Chuck. Okay, right at the end we could hear it dropping down, hear it getting quieter. But did you hear the crackle that's still in it? Okay, what we determined there, we went ahead and took this machine down. What we determined there, it had not been greased in so long that the grease had dried out. So when we pump grease in there, we were getting good grease in, and then every once in a while we'd get some dirty grease or some dried grease, and it would crackle in the bearing until we finally pumped through and got it all sounding clean. So you can even tell from there that you're getting good grease to it or not by listening to what it says, okay? So, yes, another question. Go right ahead, I can hear you.
All right, so they don't have infrared, so they just have ultrasound. I think Sean kind of elaborated on it too, but if you listen to it, the bearing's crackling, they pump a little grease into it, if it doesn't smooth out, that would be an
Write it up.
Pardon?
Write it up. Get it changed.
Okay.
That's simple. It's just
Bad bearing.
It's a bad bearing.
Okay.
Yeah. Now, and we can look at the bad bearing, and we'll do that here in just a little bit. Okay? I'm going to look at a bad bearing. We'll show you. Okay, so we've greased this motor. Let me find my stuff. I'm going to pop. This is the second motor we listened to. That's a 600 horsepower motor. Okay? This is what a motor should look like in infrared. Look at the center. The center of the motor has a band on it. You see the band right here on that motor? It's warmer right there. Anytime we have a bearing on either end of the motor, either end, inboard or outboard, that's hotter than the center of the motor, we have a bearing problem. Okay? Now people say, nah, that's crazy. But let's think about this for a minute. We've got the rotor inside of that motor. Once it's up and up to running speed, it finds a magnetic center and it's floating. It also moves axially end to end if it can, if the coupler will allow it. Okay? So basically, once the motor's up to speed, your bearings are floating. There's no load on them because it's found that magnetic center. So there's no reason for them to be hotter than the center of that operational part of that motor, unless there's a problem. Now, that problem may be a dry bearing, may be misalignment. We may have the belts too tight and we've got it pulled over into the race on that backside. You know, we don't know what the problem is, but we know we have a problem. So now we start watching this. If we start to see heat building up in the bearings, we need to take care of it. Okay? Yes?
On this motor, this warmer in the center. Earlier, the motor we looked at had a hot spot in the center.
Right.
Misaligned. How do you determine the difference?
The soft foot will be a spot. This is more a band. The whole thing here. You see, you'll have a spot where it's rubbing. Yeah, this is the band. This is the tolerances in the motor. And this motor runs 24/7 also, so it builds the heat in it, okay? So, okay, let's move on. This is real quick. I want to go through this. The bearing that we're going to look at is a bad bearing. It's a known bad bearing. This stuff is available to you. Gary and I worked this out, and it's a very simple little thing to figure out what's wrong with your bearing or how your bearing is failing. If we look at the top one, we can see that if we take 0.4 times the number of balls in the bearing times the turning speed and then divide it by 60, whatever that number is will be the fault frequency on spectralizer for the outer race failure. So now we're beginning to see that we can tell what part of the bearing is failing by using this. Okay? So let's listen to a bad bearing right quick. Hit stop, Chuck. Gary, we got to change this. Okay, here's a bad bearing. This is a known bad bearing. You hear the tonal sound in that bearing? A bassy sound? Certainly doesn't sound like air escaping. Okay? What that bassy sound is that ball coming around hitting that pit. It's doing it at 1,700 times a minute. So you can't hear between them. That's why it sounds like a hum. Okay? So if we take this, and this one here I'll take credit for. We want to put a harmonic cursor on there and find what it is. Used to be, how many of you are using Spectralizer 4 now? Everybody should get it. It's free. It's on the website. It's simple to use. Okay? And there's many things it will tell you. This one is awesome because I can go right here with my cursor hit the shift key, and that gives me the fault frequency that I have in this bearing. Okay? You see the harmonics going across there? This one happens to hit right on 91. Well, now if I'm not exactly where I need to be, I can go right down here and I can toggle up and down. Used to be you had to kind of move your mouse over and work real hard at it. I'm a PC and this is my idea. Okay? And it worked real well. It works great. I just happened to hit lucky enough to hit 91 here, to hit it right on every point. So what is 91 is my bearing failure. Okay? So let's bring up the other little chart that we showed there a while ago with the formula in it. Oops, I'm going to have to make that a little smaller. Okay. Here's our, okay, we have 0.4 times the number of balls. I know this is a 6313 bearing. It has 8 balls in it, okay? So I'm going to put an 8 right there where the balls go. The tag speed on the motor says 1750. The tag speed on the motor says 1750. So let me put 1750 in there as a turning speed. And you see what happens is magically it gives us our fault frequencies. Okay? At 1750, 8 balls in a 6313 bearing, the outer race failure fault frequency is 93. But you see we also have the inner race and the ball pass and the cage failure. Now, what does this do? It don't mean squat because I'm not replacing an outer race. Okay? I'm going to replace the whole bearing. But what it does tell me, if I have to do this 4 or 5 times, the outer race is the one that failed every time. What am I doing to this motor, or what's happening in this motor to cause that failure? Okay, so instead of just throwing bearings at the motor, let's fix the problem. Okay, well now, what was our point a while ago on that spectralizer? 91. Well, that's not right. Okay, so what's the other variable? There's only one variable here. We can't change the number of balls. Speed is all we got. Okay? So, let's drop this speed down to 1735. Well, we're getting closer, huh? Okay, I happen to know this one because I've done this once before. So, bingo! Our motor is turning at 1710 RPMs. It's not turning at 1750 like the tag says. What I contend here is the bearing has got enough wear and it's bad enough that it's putting it in a bind. It's slowed it down, the greasing problem. And the other thing is it's running under load now. That 1750 that's on the tag is bench speed. That's bench speed. No load, no coupler. Okay? No motor turns exactly what it says. All right, so now that tells me I've got an outer race failure in that bearing, which in time we're gonna prove that that's the case. I got to hurry here. I'm running out. Doug's going. Yes. Doug's going to cut my power off here shortly. So. Yes.
I thought I'm kind of confused.
You got another 20 minutes.
Yeah, I know. That's why I'm hurrying. Okay, the question?
Hang on. No, because you mentioned the 1750, the nameplate speed. That's the one that's supposed to be running at full load, not when it's...
Okay, I made a mistake there then. But we see it's not doing that. That's the point. That's the whole thing. We're not running at the speed we're supposed to be running. Because our harmonics has nailed it out. And that harmonic is that ball hitting that pit every time it goes around. So that's the only variable we have is our speed. So, okay, so let's move on to the next one. I got to get back on that screen. Here we go. Here's that bearing. Okay, I'm not going to play it again because we've heard it and we're running out of time. But let's think about this for a second. 100 horsepower motor, new bearings we can put in it. When I made this demonstration about 2-3 years ago, we could put them in for about $3,000. New bearings. Okay? A new motor maybe costs $6,000. Okay? Planned repairs, we could probably fix this for $6,000 to $8,000 on scheduled downtime. Okay? I tell the guy it's going to fail. He said, "No, we can't shut it down. The plant makes $35,000 a day. There's no way we can shut this plant down." I said, "Well, either you make the decision or the motor's going to." Okay? He decided to shut it down. When he did shut it down, when it rolled to a stop, that was it. You couldn't turn it with a 4-foot pipe wrench. The only thing that kept it running was the fact that it was running. Okay? So, let's let it run to failure. He said, "We're not shutting down." So, okay, let it run to failure. $35,000 a day his plant makes. He can't get a new motor for 10 days. Right now, we're $350,000 in the hole. Okay? Over time, plus other damage, collateral damage, we might have twisted the impeller off when it locked up or something. So we could be talking a lot more money. This job could turn into $500,000. Now, any one of you that wants to, you got good relations with your boss, you go in and tell your boss, "I'm sorry, boss. Day before yesterday, I could have fixed this for $8,000, but now it's going to cost you $500,000. You're not going to be, I don't care what kind of relations you got with your boss. You ain't going to be there very long. Okay? So that's exactly what we're talking about. Now, we brought up a thing with competitive noises, and you were asking earlier about down in the pump, okay? Let's listen to this one real quickly because it's pretty awesome. I can get rid of that one for now. I got 2 screens going here, so bear with me just a second. Oh, I got it this time, guys. Open the WAV file. We're going to listen to cavitation before it was fixed. That is ugly. Okay? But the thing we want to point out here, there's no rhythm to it. It's just like something shaking. There's no rhythm there. So there's no rhythm to cavitation. Now, what causes cavitation is we're trying to pull the liquid through the pump faster than it can come, so we get little vacuums, little bubbles in there that explode on the impeller, and that's what we're hearing. How do we stop that? I'll tell you what I done. I took the discharge that much. Actually, that much. Discharge side of the pump. Listen to it now. Here we go. That's all we done. So now, they say, "Well, I can't shut that down a quarter of a turn. I need all that production." Well, what I'm saying is, run your pump at 90% to get 100% efficiency out of it, instead of running your pump at 100% and only getting 70% efficiency out of it. Okay? Cavitation.
Gate valve.
A gate valve, yeah. It's just a discharge valve on the pump. Okay? Okay. So, we have one more here that I want to show everybody right quick. This one just came up. Variable speed drives. How many have variable speed drives? And I don't want to steal anything from James because he's going to talk about them here in a little bit. What we've been finding in a lot of water treatment plants, pumps just like this one, this happens to be a digester blower. We're finding that the rotor is building a charge and discharging that charge, partial discharge, through the bearings. It will flute the races out of the bearings. Okay? Now, how do we solve that problem? There's an easy fix. Number one, if you put your variable speed drives in right, you put a filter on the inside and a filter on the outside to stop that from happening. But if you go by the cheap way, you're just taking a chance. In this case, they didn't go they went the cheap way. This pump, when it was put in, was so far out of alignment, it was just the whole building was shaking. Okay? I told them, I said, "Guys, there's nothing we can do with this until you get rid of that vibration." So what did we do? What did we do? This is where we're hearing all the noise. Now, this is an electrical discharge. Why do we have electrical discharge on the outboard end of the pump and there's no electricity there? There's no electricity in the pump. So I called them back and I said, "What type of a coupler does it have?" It had a Nordstrom coupler with the steel shims in it. Okay? So what's happening is our charge is going through the shaft, through the coupler, out through the pump, to the outboard bearing, which is the end, and it's finally dropping off and trying to go to ground there. Okay? So what we're going to do then is they're going to take care of their vibration problem first. They picked it up and put rubber pads under it, all the way around it. Look at this. Well, it quit shaking, but it's still not in alignment. They didn't solve the problem. And now what they've done, because the conduit does not have ground straps on it, now they've isolated the total machine. There's no way it can go to ground. That's why it's cooking the bearing out on the end. Okay? So we tried to solve a problem, and we couldn't. But what we done by trying to solve the shaking problem is we created another problem. So we got to, again, use the technologies together so that we don't create more problems than we're trying to solve. Listen to this machine. Okay. I'm not going to play them all. There's quite a few of them. So we'll go to digester number 2. Let's play it in November of 2009. That's on that outboard bearing. Okay? What's our harmonics there? Looks like we could have some. Let's play with this. Let's take it down. Just keep going down. Or we can go right here and just highlight this and make it 60, because that's a pretty number. Bingo. Bingo. Electricity, huh? Electricity in the outboard bearing on the pump. That's all it can be. For that to happen to be that bearing and to go right, we'd have to win the lottery twice to get that to come out exactly that way. I will caution you though, what happens, variable speed drive, right? Okay, what happens if that's a 6318 bearing and we go back to our little chart and we bring it back up here. Remember that 1710 speed? What happens if we start dropping that down? Because remember, we're variable speed drive, okay? Well, if I drop that down to, I'm going to throw it in there right quick because I'm about ready for a cup of coffee. Uh-oh. Uh-oh. Fault frequency on the outer race is 60. What was our harmonics? 60, right? What did it sound like, guys and gals? It sounded like electricity, didn't it? Then let's go with that. So sometimes you have to pay attention to what your ears are telling you. This thing could actually be running at 1125 RPMs. And if that's the case, we could make a mistake here. Very easily. Okay? But I'm going to listen to what it's telling me. I'm going to look at the numbers and I'm going to use that as a tool. My main indicator's right here. That's why I wear the headphones. Yes, Joe?
Just curious what type of drive was on there, Chuck.
I have no idea. I haven't actually seen this machine. One of my techs, it's actually for Boulder Waterworks in Boulder, Colorado.
Because if it's got a 24-pulse IGBT drive on it, it should have a shaft around to bleed off the shaft currents on
yes.
it. And if that's,
and it doesn't.
It does not.
It doesn't.
Okay.
Okay.
Thank you.
And that's my next picture. Okay? Yes. I don't want to take away from your program, so don't. Now, we're not going to if you don't turn the mic on.
Just going to say that the VSD, most of them these days will have a dial gauge somewhere where you can see pretty easily what the speed is running at. So
yes.
If you want to be sure and you're not sure, another thing to do is just go look at that VSD.
Go look at the VSD.
It should be able to tell you, okay, the speed might vary a little bit, as you've already said, but
it's going to be pretty close. Yeah, and that's what, there's another indicator. Now, I wasn't able to do that because I literally got these sound bites and these pictures 2 days before I came down here. So that's why they're on the end of the program. So let's move away from that, and I'm going to show you one of the things that they've done. This is a grounding ring. Now, I'm not saying this is the proper fix. I'm saying this is a fix. What happens is that is a steel brush right here that clamps down over that shaft, and then that thing is bolted to the motor case. So what it does is it grounds your rotor to your motor case. Then your motor case should be grounded. Anytime you have a 100 horsepower motor or more, National Electric Code in the United States says it's got to have a ground, direct ground. Okay? Well, obviously that wasn't the case here, because we isolated it with rubber pads because we had a vibration problem. Okay? So now we're taking care of our vibration problem. We're not going to eat our bearings up, but we're going to cook them with electricity. So we created a problem. So with that in mind, if I can find the rest of my equipment.
On top over there.
Ah, here it is. With that in mind, there's just a couple of things that I'd like to close with. The first thing is please, please listen to your equipment, because you're going to hear things, and you do hear things that you're not used to hearing. Okay? And if I hear something that I haven't heard before, my first question is, what is that? Why is it doing that? What causes it to do that? Okay? I have to ask those questions. I need to know, because it could make a difference of shutting down a $285,000 a day plant or not shutting it down. And I don't want to take that liability. I am in business to make these predictions, and the idea is I have to be spot on right. I can't. If there's any question about it at all, you asked a while ago about the bearing. If it doesn't quiet down, write it up. Okay? I'm going to write it up. I'm going to put a flag on it and say, this thing doesn't sound right. Let's take precautions to be ready. Now, when we're ready, that means if it's another motor, I've got it sitting here. I've got my tools sitting here. I've got my lockout procedure sitting here. When I flip the big switch on that motor, bam, I'm dead to work on it. We're not going to wait 3 days on parts. We're going to have them all here before we shut it down. Okay? Very important. And with that, I caution everybody right quickly. I got about 5 minutes, and I want to talk about a silver bullet file. In the maintenance world today, because of the number crunchers, if you will, the theory is maintenance does not contribute to the bottom line. They do protect the bottom line, but they're not production. They don't contribute. First place cut, maintenance. The last place that needs to be cut, maintenance. Okay? Now, let's think about this. Remember the $500,000 pump a while ago? That's a silver bullet. Document everything. Everything you do, document it. Good, bad, or indifferent. Now, the good ones, the silver bullets, I'm going to keep them in the front of the file cabinet. The ones that ain't so good, average, they'll be in the middle. But the bad ones where I lost money on, put them in the back. Well, now my boss comes in and says, look, we got to cut the bottom line. I'm going to cut it right here. All you guys, you don't have a job no more. All you guys, you got a job, but now you're going to start doing their job too, and I ain't giving you no more money. Now, we all know that happens. Okay? When that happens, I need to go to that silver bullet file, and I need to pull that $500,000 pump out and lay it right here. I need to pull that air survey out where I showed that we saved $140,000 last year by fixing the air leaks. So I need to pull out those silver bullets. Now, if he asks me to see them all, I'll pull them all out. But I ain't pulling the bad ones out if he don't ask for them. Okay? So now I've got $500,000 and $140,000 that we saved on 2 silver bullets this year. Now I'm going to go to that maintenance man and say, look, I saved you $640,000 this year. This department, my personnel, have saved you $640,000 this year on 2 incidents. You name me anybody in production, operations, management, up to the president. I don't care. Not one of them can say they saved you $640,000. You can't afford to lay my people off. You need to let me hire some more people so I can save you some more money. Because that's what we've done. Now, we've just turned our maintenance department into an asset and not a liability. That's what a silver bullet file will do for you. Everybody should consider that. Okay? When we go talk to these people, we got to sell ourselves. They're not going to sell you. And I can't walk into the CEO's office with a hammer and a screwdriver and tell him I need $50,000. He's going to say, whoa, that's a high-dollar hammer. Because he don't understand anything but numbers. So we have to talk to him on his terms. The silver bullet file will allow us to do that. Okay? Stuff we offer internationally, obviously thickness test and whatever, it's propaganda. From there, I would say thank you. If there's any questions, we'll go from there.